Quantum physics is about to break one of our oldest assumptions in computing. That information is always either a zero or a one. In the quantum world, maybe isn't a lack of knowledge. It's a physically real state, and we're learning how to engineer with it. A normal computer stores information in bits, tiny switches that are either off, meaning zero, or on, meaning one. A quantum computer uses qubits, quantum bits, where each bit is a physical quantum system, like the spin of an electron or the energy level of a superconducting circuit. Thanks to superposition, a qubit can be in a state we call alpha times 0 plus beta times 1, where alpha and beta are complex numbers, describing probability amplitudes. That sounds abstract, but here's the key. Until you measure it, the qubit behaves as if it's partly 0 and partly 1 simultaneously. If you have just one qubit, that's cute. If you have 50 or 100 qubits that you can entangle, link so that their quantum states are correlated beyond anything classical probability allows, your system doesn't just store one pattern at a time. Mathematically, it holds a superposition of two different patterns at once, where n is the number of qubits. For 50 qubits, that's over a quadrillion configurations coexisting in a single fragile quantum state. Quantum algorithms, like Shor's algorithm for factoring numbers, or Grover's algorithm for searching, are carefully choreographed sequences of quantum gates that steer this enormous cloud of possibilities, so that, when you finally measure the qubits, the right answer is dramatically more likely than all the wrong ones. This is why quantum computers terrify cryptographers. Much of today's internet security relies on problems that are hard for classical machines, like factoring a 2048-bit number into primes. But the best-known classical algorithms, that would take insanely long. Longer than the age of the universe, on many machines. A sufficiently large, error-corrected quantum computer running Shor's algorithm could do it in hours or less, instantly breaking common encryption schemes like RSA. To prepare, researchers are designing post-quantum cryptography, new mathematical puzzles, such as lattice-based schemes that even quantum machines seem to struggle with. Ironically, quantum mechanics also lets us build new kinds of security that are, in principle, unbreakable by any computer. Quantum key distribution, or QKD, uses single photons, individual particles of light, to share secret keys. Because measuring an unknown quantum state inevitably disturbs it. Any eavesdropper trying to intercept the photons leaves detectable fingerprints, extra noise and error rates in the key. If the error rate is too high, the communicating parties know the channel has been tampered with and discard the key. This relies on fundamentals like the no-cloning theorem, which says you can't make a perfect copy of an arbitrary quantum state. Companies and even national networks have already demonstrated QKD over hundreds of kilometers of optical fiber, and via satellites over thousands of kilometers. Quantum technology isn't only about computing and cryptography. Quantum sensors exploit the extreme sensitivity of quantum states to tiny disturbances. Atom interferometers let ultra-cold atoms behave like matter waves. When gravity or acceleration changes their paths by even a nanometer, the interference pattern shifts in a measurable way. Devices using nitrogen vacancy centers in diamond, defects where a nitrogen atom sits next to a missing carbon atom, can detect minuscule magnetic fields, small enough to map brain activity or currents in a single microscopic wire. Future quantum gravimeters and clocks could reshape navigation, geology, and even climate science by making time and gravity maps of Earth with centimeter precision. All of this is still young. Today's quantum computers have noisy qubits that lose coherence in microseconds, and most practical systems have only tens or low hundreds of qubits. But the pattern is clear. As we learn to manipulate individual quanta, electrons, photons, atoms, we're turning the weirdness of the quantum realm into a new layer of technology that sits beneath our current digital world and quietly rewrites what is possible. Because once you can engineer the quantum, the next question is, what happens when you try to scale this fragile strangeness up to the size of everyday reality?